Hello everyone. Today we'll start with the first experiment, which is the description and identification of soils using the visual and manual procedure in accordance with ASTM specifications. 5 soil samples that we will be performing this test with are collected in these pans. We will start by determining the color, the moisture condition, and the odor of these soils. In order to reduce the uncertainty in determining soil colors, we use the Munsell soil color charts. Because if I take this soil sample and I ask you about its color, one will say it's white, another will say it's a gray. So we put a small portion of the soil in the opening between the colored chips, and with an easy visual comparison of soil samples, we decide on the color of our soil. For soil sample 1, the soil color could be either this or that, and by visual examination, this color appears to be this one, which is 8-1, and go 8-1 is a white. For soil sample 2, the color of the soil tends to be brown. And as we know that in Munsell soil color charts, each page has a dominant color that it could be red, white, brown, etc. So we go to the page where we have the brown color and we put a small portion in the opening and we compare. The color of this soil is most likely this one, which is 5-6. We go 5-6, it's a strong brown. As for soil sample 3, some particles has a dark color, indicating the presence of some organic materials. And we can see that the color of this soil tends to be reddish. So we go to the page, to the corresponding page, and we apply the same steps. We put the soil in the opening and we compare. The color of this soil tends to be this one, 4/8, which is red. Similarly, soil sample 4 is white and soil sample 5 is light gray. As for the odor of the soils, soil sample 1, 2, 3, and 5 has a usual odor, except soil sample 5, which has some unusual odor indicating the presence of organic materials. For the moisture condition of the soil, we refer to the criteria provided in the ASTM, which is based on visual and tactile examination. For soil sample 1, by touching the soil, we can see that it is dry. Same for 2. As for 3, there is no visible water, but by touching the soil, we can feel the presence of water, so it is moist. And for soil sample 4 and 5, they are dry soil. In order to know whether we have a coarse grain soil or fine grain soil, we need to identify the soil composition. That means the percentage of cobbles, gravel, sand, and fines. For soil sample 1, we can see that all particles are between 4.75 and 75 millimeter. So most likely it is a gravel. But when you touch this soil, you can see some dust on your hand. This dust is a silt, but for sure it is less than 5%. We can just say that we have a trace of silt. For soil sample 2, we can see that all particles are less than number 4, 4.75 millimeter, but the question is regarding the percentage of fines presented, because it's very hard to differentiate between particles greater and smaller than number 200. And as we discussed, that the solution is by doing the dispersion test. The dispersion test is done by taking a beaker and we fill it to 1/4 full with soil materials. Then we add water to the 3/4 full of the beaker and we stir until a homogeneous mixture is obtained. After a few minutes, we start seeing a difference in the color and in the dispersion of the soil. This layer represents the sandy soil, and for the upper layer, it represents the fine materials. Using a ruler, we take the distance and we do the calculation. For soil sample 3, we can see that we have some particles that are larger than number 4, this one and this one, that we can estimate it as 5%. The remaining could be either fines or sand. Again, we do the dispersion test for the soil to identify the percentage of each component. Soil sample 4 is called Ottawa sand. It is purchased in a bag because it's a naturally rounded shaped particles found in Ottawa in Canada, characterized with a uniform gradation. The importance of this soil is through validating our experimental results. What does this mean? When you are testing the soil collected from your site, for example, and you need to verify that you are doing the experiment correctly with all equipment well calibrated, then the solution is to do this experiment first with Ottawa sand and compare your results with the range that Ottawa factory provided. If you are within the range, then you are doing the experiment with the proper way. And this is very important in your discussion later on when we will be working with Ottawa sand. For example, we are getting the specific gravity of the Ottawa sand. You get a number, go search for the range, the acceptable range. If you are within this range, then you did your experiment correctly with no errors. For soil sample 5, it looks like flour, so we can conclude that all particles pass at the number 200 sieve. After we finish the first steps, we were able to classify the soil samples in two categories: coarse grain soil and fine grain soil. For soil sample 1, it's a coarse grain material. So we take a sample and we spread it on a flat surface. We know that the threshold between fine and coarse gravel is the 19 millimeter. And by looking at all particles, we can see that all of them are smaller than the 19. So we have 100% fine gravel. For the shape, 1/3 of the gravel particles are elongated. The others don't meet the criteria provided in the ASTM. But if you can note anything else, you can put it on your report because we said that it is subjective. As for the angularity, we see that we have some particles that have a sharp edges and other that are similar to angular description but have rounded edges. So we note that the angularity of the gravel is angular to subangular. As for the gradation, we can see that particles have somehow an assorted of size, so it is well graded. For the maximum particle size, and because we are dealing with gravel, we need to use different sieves opening. Here we used the 3/4, half, and 3/8 inches, and we found that all particles pass the 3/4 inches square opening, but some of them retain on the half square opening. For the hardness of the particles, we see that all particles do not crack, fracture, or crumble under a hammer blow, so we reported as hard. For the HCl reaction, we added the hydrochloric acid to the soil particles and we observed a violent reaction with bubbles forming immediately. So we described this reaction as strong. Now for soil sample 5, which is a fine grain soil, you will notice very different behavior when you add water. When the soil is dry, it acts like a solid, but as we continue to add water, the soil becomes sticky and soft, exactly like a gum, which is referred to as the plastic state of fine materials. Starting with the dilatancy test, we take a ball of about ½ inches diameter and we shake it horizontally. Then we note the reaction of water appearing on the surface of this ball. In our case, we have no visible change in the specimen. For dry strength test, we make at least 3 test specimens. A test specimen shall be a ball of material about ½ inches diameter, and we allow the test specimens to dry in air or sun as long as the temperature does not exceed 60 degrees Celsius. When the ball is dry, we do the following step in this order until the specimen crumbles. First, we apply some finger pressure, then a considerable finger pressure. Then we try to break it between thumb and a hard surface. In our case, the dry specimen cannot be broken between the thumb and the hard surface. For toughness test, the test specimen is shaped into an elongated bat and rolled by hand on a smooth surface or between the palms into a thread of about 1/8 inches in diameter. We note the pressure required to roll the thread near the plastic limit, which is the 1/8 inches, and also we note the strength of the thread. For soil sample 5, a considerable pressure is required to roll the thread to near the plastic limit, and the thread and the lump have very high stiffness. You can notice that rubbing my hands together will not clean them. I need to put my hands under water in order to cleanse them.